In this video, we're going to talk about the second law of thermodynamics a little bit, and specifically what we mean when we say thermodynamic reversibility. And this becomes a really important concept when we're talking about the performance of real systems, this concept of reversibility. But the thermodynamic definition is a little bit different than maybe what we speak of colloquially when we use the term reversible. So we'll dive in a little bit more to what we mean by reversibility and the second law. So the second law of thermo, just a kind of rough definition that we've used so far in class, is that heat won't spontaneously flow from cold to hot. Right? Heat only flows one way, and it's from hot to cold. The first law of thermo, right, conservation of energy, gives an equality. Right, it gives us balances. It says that energy is conserved, so we can write the amount of energy at the final state is equal to the amount of energy in the initial state. The second law, on the other hand, gives an inequality. Which makes it a little different, and it means that we have to deal with it a little bit differently. So the second law really defines the limits. It defines the best possible process. And we call this best possible process, right? So a process meaning something like a pump or a heat transfer or anything happening, really. It defines the best that we could possibly do. We call this best possible process a reversible process. So a reversible process, we'll define it a little bit more in depth here in a second. But this reversible process sets a maximum. Right, it's the best possible, so it's a maximum. This is what we mean by an inequality. It's a maximum for the conversion of thermal energy into mechanical energy. So thermal energy, we're talking about things like heat. We've used the variable Q, or internal energy. Right, which is the thermal energy associated with matter. It's internal energy. And for mechanical energy, we're talking about things like flow work, right? Which would be workflow is pressure times volume. Potential energy. Kinetic energy. Or shaft work. So the second law gives us a reversible process, and that reversible process sets a maximum for the conversion of thermal energy into mechanical energy. So just two more definitions, really saying the same thing, but to drive that home. A reversible process is one that converts the maximum amount of thermal energy into mechanical energy. This would be a work-producing process. Something like an engine. I apologize. Then the flip side of that is it converts the minimum amount of mechanical energy into thermal energy. This would be a work-consuming process, something like a pump or a compressor. A reversible process requires balanced forces. And I'll underline that a couple times because that's really important. And we'll dive into a little bit here in a second what we mean by balanced forces. It's and probably the easiest way to really unpack that is by looking at the other side of the coin. What does an irreversible process look like? So an irreversible process is one which is caused by two different things. One would be dissipation, right? This is something like friction or electrical resistance. And I think this is easy to understand, right? If we have two processes and there's one which has no friction and one which does have friction, it's easy to understand that friction would reduce the performance compared to a system without any friction. Same with electrical resistance. If we compare a process with no electrical resistance, that's clearly better than one with electrical resistance. Now this second point, unbalanced forces, is a little bit harder to unpack. So I'm going to give a couple examples and then we'll look at a little video showing it. So the first example is unrestrained expansion, would fit under this concept of unbalanced forces. So if we imagine a situation where we have a box. Let me draw that a little bit better. So we have a box like this, and right down the center of the box is a wall, and on one side is a perfect vacuum, so there are no gas molecules on that side. On the other side is air. Or let's say, for the sake of this, let's say it's nitrogen, N2. Okay, so we have this box. Now, there are two different ways, two different paths we could get from, there are more than two, but let's consider two paths, where we could get from this initial state, we'll call this state 1, to a final state, state 2, where now in our final state we have our same box, but now the entire box is filled with nitrogen. So this first path here would be a reversible path. In our reversible path, and let me change colors here, sorry, just to make this a little bit more clear. So our reversible path here would be something where we have a gradual expansion, right? We would have balanced forces, so we're slowly moving the wall. And as we do that, we would be extracting work from the system, from that expansion. So slowly moving wall. extracting work. That's going to be our reversible path. Likewise, an irreversible path would be one where, now there are more than one, so this would be the most irreversible path. Again, to the same state where our box is entirely filled with nitrogen. The most irreversible path is we poke a hole here, and we don't capture any work from that expansion. Or no work extracted is probably the better term. Okay, and these are two examples. One where where we're moving that wall, we would have a slow and kind of gradual expansion, and one where we poke the hole and we let it go kind of as fast as it can. One where we extract work, and one where we wouldn't get any work at all, but we still get the same expansion. We get the same final volume, but the path would be really different in these two cases. In this top path, the green path would be our reversible path. The bottom would be an irreversible path. Let's jump to a diagram of another example. Hopefully it will make this more clear. All right, so we've jumped over to PowerPoint, to this PowerPoint slide. Again, hopefully this will make it a little bit more clear. In this case, we're not doing an expansion, but this would be a compression. And we're going to look at two possible paths to do a compression. In both paths, we're going to be adding 100 kilograms on top of this, this piston. Right? In both cases, we're putting 100 kilograms on top of that piston there. In the first case, we do that by dropping our weight on there instantly, and there's just like, right, all of a sudden we have this huge force, right, about 1,000 newtons applied right away, and it causes the compression for the gas. In the other case, we have grains of sand, and we're going to slowly add grains of sand on top of our piston until we get 100 kilograms of it. Now the process on the left is more irreversible because what's happening is we have, right, this really big force being applied. If we look at the gas as our control, the surroundings, this 100 kilogram weight, is being applied very rapidly when we drop the weight on it. So it's pushing down with a force of about 1,000 newtons, but the gas is not pushing up with the same force. Okay, so there's a big difference between how hard we're pushing down on the gas versus how hard the gas is pushing back. That's causing irreversibility. Now in the example on the right, because we're adding sand a grain at a time, we're pushing down with just a tiny bit of extra force on the gas. And the gas is able to be able to respond to that, and it compresses a little bit, and then is pushing back with, again, the same force. And then we throw the next grain of sand. It compresses a little bit, but it's just by a tiny little increase in the amount of force being applied. So every time we're adding a grain of sand, despite the fact that we get to 100 kilograms still, we do it by the gas pushing up at almost exactly the same force as the sand is pushing down throughout the entire time that we're adding sand. All right, so now we're back to the notes. The next way, and we'll explore this a little bit later, a little bit more in depth next week, is heat transfer through a finite temperature difference. So if we have, right, let's say that, you know, in this direction we have a higher temperature. So if we have a, say a temperature here, T hot, and a temperature down here, T cold, we can have heat, Q, flow that way, from hot to cold, but it cannot flow backwards because obviously that would violate the second law. So we can flow one way but not the other. So this would be irreversible. A reversible system, again, that's the y vertical axis is temperature. We have T hot, and T cold is the exact same. In a reversible one, it's the exact same temperature. And then we can have heat flow from hot to cold, but because they're the same temperature, we can just as easily have heat flow from cold to hot because, again, they're the exact same temperature, so heat can go both ways. Obviously, right, reversible processes, maybe you can understand, they don't actually exist in real life. Right, we need some sort of temperature difference in order to have heat flow at all. But we can imagine, right, the bigger the temperature difference, the more irreversible that heat transfer is going to be. If we have a small temperature difference as we approach the case on the right, that's going to be closer to reversible. Now, the last case we'll talk about is mixing. And this is really a kind of a special case of the first point of an uncontrolled expansion, or an unrestrained expansion, where if we go from, right, if we take this case and we poke a hole in the middle, eventually we'll get to, right, a point where, let me draw the hole now, we have N2 plus O2 on both sides. Right, if we have, these gases would eventually mix, and we couldn't bring them back to their initial state without adding in extra work. So that's kind of the defining feature of a reversible process. We don't have to add in extra work to get from the final, from state 1 to state 2, state 1 to state 2. If we go along a reversible path here at the top, we're going to get work out, and we could use that same exact amount of work to go backwards and push our wall back to where we have a vacuum on one side and nitrogen on the other. Irreversible paths are ones in which we can't get back to the exact same starting point without adding in extra work. So a mathematical statement of the second law would be that the sum of the entropy final, and this is the sum of the universe, right, all of the entropy in the universe, minus the sum over the entire universe of the initial amount of entropy is always greater than or equal to 0. So it's exactly equal to 0 in the case of a reversible process, the best possible process. We never can actually get that, so it's actually always going to be greater than 0. A more philosophical statement would be maybe something like entropy always increases, it can never decrease. So both saying the same thing. Now, just a special thing to note, this is talking about the entropy of the entire universe for a reason. So when we're dividing up, say, looking at a slice of the universe in a control volume, we're not looking at the entire picture. So it's important to remember that we're not looking at the entire picture. And in order to, for this statement of the second law to be true, we need to be looking at the entire picture, both our system, say our control volume, but also the surroundings too, in order for the second law to be valid. So there are a few special cases where we can actually know what happens with entropy, and these will be important special cases as we go on. So for a reversible process, right, a reversible process is one of these processes that forces are balanced all the time. It's the best possible process. For any reversible process, we can write that that a differential change in entropy is equal to a differential amount of heat transfer divided by the temperature. Okay, this is kind of a weird way to write things. We'll write the integrated form. That's maybe a little easier. So an integrated form is that the amount of heat transfer which occurs during that reversible process is equal to the integral of TdS. Right, this is Q as the heat transfer that's occurring during that process, whatever process it may be, is equal to the integral of TdS. If we have an isothermal and reversible process, right, isothermal meaning temperature equals constant, so a constant temperature and reversible, then we can see from our equation above, right, Q equals the integral of T ds, but this is just a constant. So Q equals T times the integral of ds, or Q equals T delta S. Okay, so that's one special case, isothermal and reversible. This is kind of our first special case, reversible. And our last special case is one that we've used before in class, adiabatic. That's where Q equals 0. And then we have 0 equals the integral of T ds, which means that delta S is equal to 0, right? The only way that this equation can be true is if the integral of ds is 0. So these are three special cases. We'll use especially this last one, the adiabatic and reversible process, but we'll also use the other two as well as we think about entropy and processes and how these things are related.